think this one is like what y'all did? Yes? Okay.
That looks
All right.
eerily familiar.
Okay, so I1,
Do we have a
I see.
frequency?
what's that?
Do we have a frequency? Oh, yeah, sorry.
Yes, 60 hertz. There's a frequency. Yeah, so while we're getting started on this, whoops, there we go. If anybody has free time and calculator, if y'all wanted to be getting the phasors of the impedances, that would be useful. Okay, so around loop I1, I will have minus 30 plus 10 I1 plus, I'll call this L1 and L2 for right now, J omega L1 I1. And then I have a mutual impedance between these two inductors that's being caused by I2. Now, because our current went in the dotted side and I2 went in the dotted side, the sign of the mutual impedance is the same as the sign of the self-impedance. So it will be plus J omega 0.2, but times I2 equals 0 for the equation for our first loop. And let me just double check that and make sure I have it right. It looks like I have it right. Okay. Where did I get the 0.2 from?
Mutual impedance.
Oh, mutual impedance. Okay, and then for the second loop,
I think you forgot oh, sorry, you just wrote it in as L1.
yeah, I just put it in as L1. And then for the second loop, I will have I2 times 200 plus J omega L2 I2, and then I'll have the mutual inductance that's caused by I1. Since I2 is going into the dotted side and I1 is going into the dotted side, the mutual impedance will have the same sign as the self-impedance, so it will be plus as well. So it'll be plus J omega 0.2 times I1 equals 0. Now let me double check that one. J omega I2, J omega 0.2, yep, those look right, okay.
This is screaming Kramer.
It's screaming
Kramer's rule.
TI Inspire CAS.
Oh, I wish.
So minus 30, so this is plus 10 J omega, so omega is 377, L1 is 10, so that's 3,770. So plus J 3,770 I1. What?
It's 10 milli, so it's 3.77.
It's 10 milli.
10 millihenries.
10 millihenries. I was looking at the wrong one. I was looking at the yeah. So I was thinking that L was 10, but L is 10 milli. So that would be 3.77.
Yes.
3.77. And then plus j omega is 377 times 0.2 is
75.4.
75.4. J I2 equals 0. That's the top equation. And then the bottom equation is 75.4 J I1 plus 200 plus J 377 I2 equals 0. And then you have a system of two equations and two unknowns to solve that I'm not prepared to do like in front of people because I'll make too many mistakes. But this is the EE part. The rest of this is math.
And that's all.
You don't know Kramer.
After you find I, then you just turn it into its.
Well, I think the problem was to find I. I never said what the problem was.
When they said find I, is that specifically I2?
Yes.
Okay.
Well, you can see that we
Yes.
defined I2 to be the same
Yes.
direction as I of T.
Yeah, I of T would be I2.
Can you like describe how the current flows in that type of circuits? And like
Sure, it flows like the way you're seeing it here.
so like it's just two separate circuits
It is, but they affect each other
because of the two inductors.
because the inductors, right, they have mutual inductance.
We're finding I.
So the only difference is that you can
We add a term in when we do the KVL from the inductor, from the other inductor. So when you see this right here, that is telling you that you have mutual inductance. That means any current through this other inductor affects the first inductor. And it does it by taking the mutual inductance as a phasor, and so it's going to be J omega L, just like any other J omega L, and you multiply that times the other current, and that becomes an impedance on the loop. So anytime you have a current going through an inductor, you get an additional impedance from other inductors that are around if they have a mutual inductance. So we got not only the self-inductance term, which was J omega L1 I1, we also got from this same inductor, we got the mutual inductance term right here, which came from the fact that these inductors interacted with each other. And so this term, it gets the 0.2 is because of the mutual inductance, and then the I2 is because it's going through another
I see
inductor.
What you mean. That's why whenever we're solving for the mesh and the 0.2 would be I1.
It was I1,
Okay.
right.
I see what you meant now. To its okay.
And you actually can do that when you have like other inductors in there too, which is the problem I started to do when y'all said no, you never did one like
Yeah,
that.
I can see why we use mesh. So it makes it by it.
Yeah. And so if you want to know what the answers are, they are,
I would love to, yes.
I have the equation to find it. But I don't feel like.
it's 0.293 angle negative 125.8. Let's do the second part of the problem, which said,
We should be allowed to use MATLAB circuits.
and the second part of the problem, which I did not tell you what it was, said to find the average power absorbed by RL. So
That's how you would set up Kramer's rule for this. Is you put your constants for the thing you're not finding. Or, sorry, for the thing you are finding, yeah. You want the regular numbers for the thing you are. No. We have two unknowns, and the other current is one of them.
Okay.
For this problem, we're solving for I of t, which is xt.
So if I want to find the power absorbed by the 200 ohm resistor, then that's going to be just the real power because it's a resistor. And since it's just real power, I don't have any of those extra formulas memorized. I know that power equals IV. I know that V equals IR. Since we're talking about a resistor, I know it's going to be real. I know that what is meant by I squared is going to be the magnitude of I squared times the resistor. And so the power absorbed by the resistor is going to be the magnitude of I2, because I2 is the current going through this resistor. And that magnitude was found to be 0.293 squared times 200. And that would get me, except I forgot my 1/2. I forgot my 1/2 because it's not RMS. And so then the answer after that is 8.57 watts.
We're at 8.59.
Or rounding, but that's usually
It'll
better
round,
calculate.
it'll round some way or the other.
All right.
I've always found that those round weird. The 84s.
All right. So moving along, let's go on to find. This is this is straight up chapter 7. Just it's not power. It's just using complex circuit analysis. So find VAB given that IS of t is 35 sine 300 t minus 15 milliamps. That's milliamps. Don't forget that because I will. R is 80 ohms, L is 15 millihenries, and capacitance is 200 microfarads. Okay, so I want to find VAB. So I know what I would do here. What would y'all do here?
Current
Law,
division.
current division, and then law.
I would just find the parallel impedance and then solve it for that. You don't.
That is,
I would take
that's,
the problem.
everyone should do that.
Yeah, I think. Do I just know what the answer is? Hold on.
Is the rest just going to be like review from the rest of the chapter?
It is. I do have like videos of other stuff if you
Yeah. So.
needed to see it. Let's see.
You would just be able to find the parallel impedance.
Yeah.
Yeah,
Yeah.
yeah. But I am. No, I can't do that. Okay, I wanted to do it like super easy and just do a source transformation, but I can't do that because
No.
if I do a source transformation, I'm transforming the actual thing I'm trying to measure, and you can't do that. So, so there are two ways of doing it. You could find the parallel impedance, or you could do current division and then Ohm's law. And I am tempted to do. What am I tempted to do? Well, first thing I'm going to do is get all these as phasors. So the current is going to be 35 or 0.035, angle negative 15. R is 80. C is minus J over 300 times 200 times 10 to the minus 6, and L is J times 300 times 0.15. And that gets me, it's times 10 to the negative 6. So I have negative 16.67 J, and y'all check me on these, for the capacitor, and J45 for the inductor. And so what I want to do is take 0.035 angle negative 15 times I will do
Shouldn't
80.
you use the cosine?
Oh, I should. That was rude of them. 300 minus 105 degrees. Or am I supposed to add 90?
You subtract 90.
You do subtract 90.
Yeah.
I agree.
So 105. So it's
I'm glad
30.
you understand. You're right.
It's 35 minus angle 105 degrees. So it's cosine. Thank you for catching that.
Up in-
I put a little 0 in there between the 1 and the 5. 105 degrees. So negative 35 times 105 times 80 over 80 plus J 28.33 gets me the current through the reactive side over here. And then if I multiply that by the capacitor and the inductor, if I multiply that by J 28.33, that should give me the voltage. So what I have right here, this is the current through the capacitor and the inductor because of current division. So current division would take my total current times the impedance of the other branch times the total impedance, and the total impedance is all of them added together. And so that would give me the current through this branch. And then I multiply that times the impedance of that branch, and that should get me the voltage. And let's see if it does.
So it's just multiplying by the power.
Yeah, I just did it all in one step because if I'm going to make a whole lot of mistakes doing calculations, I might as well do them all at once. And then there'll be no way to tell where the mistake is.
That's how they think.
Negative 105 times fraction 80 over 80 plus J 28.33 times J 28.33 and the answer's not right.
I think you add 90 to the angle, you subtract it. I got 0.0935 angle negative 34.5.
Yeah, isn't that supposed to be 4.5, not 0.5?
let's see, the sine of 0 is 0. The cosine of negative 90 is 0, but so is the cosine of 90, so that didn't help me. So the sine of 90 is 1. The cosine, I subtract 90. Yeah, because, yeah. So sine of 90 equals 1. So if I wanted to change that to cosine that had the same value, do 90 minus 90 equals 1. Yeah. Subtract 90. So that's not my problem. So what is my problem? Did I do... Well, I could copy the problem correctly. It says 200 microfarads, and I put in 300 microfarads.
You put in 300.
Oh, no, that's the omega. Never mind. So omega is 300.
So you would subtract
No, no,
90.
no.
What is what you're saying?
No, it's one. It's already subtracted.
That's not already
No,
subtracted.
no.
Okay, minus 16.67J plus 300 times 0.015J.
Wow, this is stupid. I think it's gonna-
No, I'm pretty sure that I did it right. But what I did not do right was the following. So, 15 millihenries is, obviously 0.015 and not 0.15, and that's my mistake. So, 300 times 0.015J is 4.5J, not J45. And then if I add to that my 16.67, or my negative 16.67, I get negative 12.17J. Then if I do the same calculation, I get the right answer. Not the right angle, but they have an angle over 180 degrees. I get the right angle. So this equals 0.42 angle 173 degrees volts, which they gave as negative 186 degrees volts.
No matter if you add or subtract, it's a difference of 187.
It does
The difference
matter.
of 180, but it was a negative, but you did your thing.
It does matter. You do get the wrong answer if you do it that way.
Negative 6.35.
Okay, so that was a lot of messy work, but it was, the idea was just that, to find so the main idea is just that you have to be able to convert your impedances to phasor. And so a capacitor, you convert it as minus J over omega C. An inductor, you convert as J omega L. You are careful and you realize that 15 milli is 0.015 and not 0.15. This one was sneaky with the sign. I don't think he would give you one of those, but if you do, you subtract 90 to get it to be in terms of cosine. Yes?
What was the final answer?
It was 0.42 angle 173 degrees.
Think positive.
0.42?
Yes,
Okay, I got 0.43.
Yep.
So what was the angle?
173
Positive?
positive.
Okay.
And the solutions manual says negative 180 something.
That's
which,
exactly what was, yeah.
Yeah, but it's the same. But you would add 360 to get it to be the 170 term. Okay, let's do this one. This one is just simple, complex arithmetic if you can do it, which I'm not convinced I can. So this would be 0.002 farads, which I'm going to change in a minute. I just wanted to make sure that I don't mess up my powers of 10 here. And this is 0.01 farads. And so F is 60 hertz, so omega is 377. That comes from omega equals 2 pi F. The reason I know that it's 377 is 60 hertz just shows up a lot because that's the frequency of our AC. And so this is minus J over 0.002 times 377. This one is minus J over 0.01 times 377. The resistor stays nicely as 3 and 8. And this is going to be 0.2 times 377 J. And then
Is Z just the total impedance?
yes, just the total impedance. Oh, I don't have the answer for this one. Good. That way I don't have to worry about if I make a mistake because I'll never know. So this would be,
Prefer if he doesn't.
I'll try not to. 0.002 times 377. So this becomes minus J 1.326 and this becomes J 75.4. This stays 8. This stays 3. And this becomes J.265. So then we can say that we have minus J 1.326 in series with two impedances that are in parallel. This one is 8 minus 8 plus J 75.4, and this one, there was a minus, was 3 minus J 0.265. So then the two that are in parallel, I can find their equivalent by doing 3 minus j.265 times 8 plus j75.4 over 3 minus j.265 plus 8 plus j75.4. So we can get that. I think I can add 3 and 8 and get 11, but I'm not entirely sure. I get, as a phasor, 3.007 angle negative 2.77. .775. As rectangular, that was 3.004 minus j.1456. So that is the equivalent impedance of the two in parallel. And then to get our total impedance, we still have to add in this last capacitor that was in series. So I'll take the 3.004 minus j.1456 and add in minus j1.326 to get our final answer. Of, as a phasor, 3.34 angle negative 26.1, and as rectangular, it'd be 3 minus 1.47 J. Ohms. Impedance is in ohms. Okay, so that one, not terribly exciting, but he has given problems like that on finals sometimes. So you sometimes see that.
Where is it for this question?
What's that?
Nothing?
Can somebody, I need some light.
Wow, apparently I don't exist very well.
Often I hide that. Look how often I hide it. Listen, the father corrected the figure
That's hilarious.
What's that?
I always spell forgot with an R at the end instead of a T, so it's for gore. And I've done it so much that's
It's
the
autocorrects.
autocorrect.
I have things like that. Okay. All right. I really should make a new video for this, but I'm not going to. I'm just going to keep recording on this video. No, I'll make a new one.
Just
No, I
to let you
won't.
know, there's one power question you skipped. You think you might do that like in the end?
Which power question did I skip?
It was like the circuit we did. It's question 4.
Question 4. Did I not do this one?
No, we did one where the, yeah, we did a different one.
Did a different one. Okay.
We went through a couple others.
Okay. Well, we
We
can.
were looking for one that had,
Well, this is
that
this
had-
this one's
that
easy.
had a couple more, yeah. No, we were looking for one that had reactive impedance on both sides.
Okay. I have time? Do I have time? I don't have time. I actually have to go. So I will see if I can get these up for y'all, the rest of them up for y'all later. So I have to go. So sorry about that. Bye. Thanks for coming, guys. I gotta go.
Inductive work capacity?
But I will try to get the rest of these up for y'all later.
Yeah, it's like an overarching term for any imaginary influence.
It's probably the last time I see you though.
What's that?
It's probably the last time I'm gonna see you.
No.
Sad.
Is it like any different?
Oh yeah, because I'm not taking sixes, so.